To introduce the algorithms for minimum spanning tree, we're going to look at a general algorithm called a greedy algorithm. It's a good example of a general principle in algorithm design that will help us prove correctness of our algorithms. To begin, we'll make some simplifying assumptions. First, we assume that the edge weights are all distinct and that the graph is connected. And this is just to simplify the presentation. As a consequence of these two assumptions, we know that the minimum spanning tree exists and is unique. Our algorithms will still work when edge weights are not distinct. If the graph is not connected, it'll find spanning trees of components, but these two assumptions simplify the presentation. Now, to understand our algorithms, we're going to start with a general operation on graph called making a cut. So a cut in a graph is a partition of its vertices into two non-empty sets. And we'll indicate that just by coloring some of the vertices gray and others white. So that's a partition into two sets, the gray vertices and the white vertices. Every vertex is either gray or white, and there's at least one in each set. Now, given a cut, a crossing edge connects a vertex in one set with a vertex in the other. So every edge that connects a gray vertex to a white vertex is a crossing edge. So that's a second definition that gives us a way to talk about edges and graphs when we compute the minimum spanning tree. So an important property that is relevant to MST algorithms is that given any cut at all, the cut defines a set of crossing edges. The minimum weight crossing edge is in the MST. Remember, no two edges have the same weight, so there's a single edge that has minimum weight from the edges in the cut. So in this case, the thick red edge is the minimum weight. It's the shortest edge connecting a gray vertex with a white one, and that edge has to be in the MST. That's the cut property. Here's just a quick proof of that property. I'll hand wave a bit through the discussions of the proof. It's usually not appropriate to fully dimension proofs in the lecture, so you should look at the book or the online materials to be sure that you understand the proofs or reread these slides. But I'll try to give all the steps. So we're trying to prove the cut property, giving any cut the crossing edge minimum weights in MST. So let's suppose the contradiction. So suppose that we have a minimum weight crossing edge that's not in the MST. So in this case, that edge E, suppose, is not in the MST. It means that one of the other crossing edges has to be in the MST, otherwise the MST wouldn't be connected. Then if you add E to the MST, you get a cycle, and some other edge in that cycle has to be a crossing edge. That's the way to think about it. Remember, MST is the minimal way to connect the graph, and if you add an edge to a tree, you get a cycle, and then there's some other edge that has to be a crossing edge. But if you remove that edge and add E, then you're going to get a spanning tree, and that spanning tree is smaller than the one that you had. So that supposition had to be a contradiction. So it has to be that the minimum weight crossing edge is in the MST. So that's the cut property. Now given that property, we can develop what's called a greedy algorithm, which is the easiest algorithm we can come up with. So what we're going to do is start with all edges colored gray, find any cut that has no black crossing edges. The algorithm's going to color some of the edges black, and color the minimum weight edge of that cut black, and just repeat the algorithm, finding any cut with no black crossing edges, color the minimum weight edge black, and keep going until you have v-1 edges that are colored black. And the claim is that that's going to compute an MST. Let's look at a demo of that just to make sure that we follow what's going on. So we start with all edges colored gray. We're supposed to find a cut with no black crossing edges and color its min weight edge black. Well, that could be any cut. In this case, we'll take the cut that has 3, 2, and 6 on one side, and 1, 0, 0, 1, 4, 5, 7 on the other side. Look at all the crossing edges. Minimum weight crossing edge is the one from 0 to 2. So that's the one that will color black. So now we have 0, 2 on the MST, it's colored black. So again, any cut that doesn't have a black crossing edge. So in this case, let's do the cut that just has 5 on one side and all the others on the other side. In this case, there's 3 crossing edges. The smallest one is 5, 7, color that one black. Again, any cut that has no black crossing edges. So let's just take 6, the cut that has 6 on one side and all the others on the other. 2, 6 is the minimum crossing edge. So 6, 2, and so we put that one on the MST. As we get more and more black edges, it's going to be harder to find a cut with no black crossing edges, but we press on. So now let's do the cut with 0, 2, 4, and 6 on one side colored white, and 1, 3, 5, and 7 on the others. So there's a lot of crossing edges in that cut, but the smallest one is the one between 0 and 7, so that's the one that we color black and add to the MST. So now we have 4 edges. Next cut, 1 and 3 on one side. Smallest edge in that, the smallest crossing edge for that cut is 2, 3. Now one more. Now let's put 1 and 4. Now almost all the edges left are crossing edges. So 1 and 4 on one side, all the rest are in the other. And the minimum weight crossing edge is the one from 1 to 7. Notice in this case we got the nodes in the tree on one side of the cut and the nodes not in the tree on the other side of the cut. One of our algorithms will always have that property. So now we add 1 to 7, 1 and 7 to that, and now the last thing is the only cut that has no black edges is the one that puts 4 on one side and all the rest on the other, and the minimum weight crossing edge for that one is 5, 4. So now we've got 8 vertices and 7 vertices in the 7 edges in the MST. So we've found the MST. We've got V-1 edges colored black, and we've found the MST. So the greedy algorithm is a very general algorithm. We're allowed to find any cut at all that has no black crossing edges. So let's do the correctness proof, and then we'll look at some specific instances of the greedy algorithm. First of all, since we took the minimum crossing edge of a cut always to color black, any black edge is in the MST. That's the cut property. Do a cut, no black crossing edges, you can color it black. That's in the MST. So that's first observation. Now, when we have fewer than V-1 black edges, there has to be a cut that has no black crossing edges. That is, the algorithm doesn't get stuck. And so the way to think about that is just take the vertices in one of the connected components and make that the cut. Then there's going to be, since that's the connected component, there's going to be no black edges in the crossing edges for that cut. So the algorithm doesn't get stuck. If you don't have an MST yet, there's going to be some cut with no black crossing edges. And that's it. The greedy algorithm computes the MST. Any edge colored black is in the MST, and you can always add to the set of black edges if you don't have V-1. Once you have V-1, you've got V-1 edges that are in the MST. The MST has V-1 edges. Greedy algorithm computes the MST. So now what we want to do is implementations of the greedy algorithm or specializations of it really that differ in, first of all, the way that they choose the cut, which cut are we going to use, and also the way in which they find the minimum weight edge in the cut. Again, those could both be expensive operations and prohibitively expensive for huge graphs. What we're going to look at is two classic implementations called Kruskal's algorithm and Prim's algorithm, although in both cases we use modern data structures to make them efficient for huge graphs. And there's another interesting algorithm called Borufka's algorithm that kind of combines the two, briefly mentioned. Now, before getting to those, what about removing the two simplifying assumptions? So what happens if you have a situation where the edge weights are not all distinct? So in this case, 1, 2 and 2, 4 both have the same edge weight. Well, so also to 1, 3 and 3, 4. And so it means there's multiple MSTs. So in this case, there's two different MSTs. So the greedy algorithm is still correct, it turns out. Our correctness proof doesn't quite work, but that can be fixed with a little bit of work. And so the fact is it's still correct. And if the graph is not connected, as I mentioned, what we'll get is what's called a minimum spanning forest, which is the MST of each component. Essentially, it's like independently computing the MSTs of the components. But basically, what the greedy algorithm gives us is an easy way to prove correctness for specific algorithms. All we have to show is that they're finding a cut and taking the minimum weight edge from that cut. And then we can prove correctness of a more complicated algorithm. In general, in algorithm design, this is proven to be effective in all kinds of domains. Trying to come up with a general algorithm that you can prove works efficiently, and then using that to help design specific ones.
The point is, ladies and gentlemen, that greed, for lack of a better word, is good. Greed is right. Greed works. Greed clarifies, cuts through, and captures the essence of the evolutionary spirit. Greed in all of its forms. Greed for life, for money, for love, knowledge, has marked the upward surge of mankind, and greed, you mark my words, will not only save Teldar paper, but that other malfunctioning corporation called the USA. Thank you very much.
Let me play among the stars.